General Relativity Part 4. We are going to talk about everything tensors. Well, not everything tensors, but a lot of things tensors. General Relativity Part 4. Alrighty. Last week. Again, if you are new, !Discord.
Welcome to the channel.
Ooh, here we go. A little bit weird. Assault Rabbit. Welcome to the channel. Thank you for the follow. !Discord will take you to the Discord, and in the General and Special Relativity sub channel, you can find notes for today and last week and every other week. So, the note from last week, what we talked about last week was vectors, and we could establish vectors as as tangents to the manifold, right? Every manifold will have a tangent space to it, and that tangent space is made up of vectors. And those vectors are the ones that we're interested in, and we talked about them. And then there's also a cotangent space with dual vectors. We talked about all of that, and we found out that the dual vectors are linear maps onto the vectors to get real numbers. And that was what we saw as an and that is what we saw as a I don't want to write this definition because I'm going to use a different definition in a second here. But that's what we saw as like the inner product, right? What we used to know as the dot product. We're graduating. Calc math told us to forget the dot product. So we want to get rid of the dot product. It's no longer a thing for us. Now we're talking about inner product, and this inner product was this relationship between mapping the dual vector onto a vector, right? Now, that was a useful tool for us, and I think I want to recast what the definition of vector is what Hartle says, but we'll get there in a little bit. So right now, and we'll have to talk about it more, but basically this week is all about tensors. Last week we talked about vector notation, so we did the tangent bundle, the tangent space, the vector field, the vector. We did all that stuff, and now it's time to move on to tensors. So last week we did all. Yeah, I already said all that. Cool. And now, so we want to figure out a linear map from vectors to real numbers that is useful, but we need a generalization, right? Before, the only generalization we had was dual vector onto vector gives you real numbers. But what is there anything else? But the inner product is something, so we have, so is there a way that we can do a more generalized form of that? It would help to do a recap as a written recap. Okay, sure, I can write some stuff down. I didn't actually put it in the notes, but I can write it down on the board right now. So we established that there was so we were talking about flat space-time. We had our four vectors, where the four vector components look like this. And then each of the components, where the Greek letters ran from 0 to 3, and each of the components look like the following. X of 0 is equal to ct, or we set c to 1, and then it's the time dimension. And then x1 is equal to x, x2 is equal to y, and x3 is equal to z. So that was one thing that we've talked about before, where we just have this Cartesian setup, or we had this setup in Minkowski space, flat space-time. And this flat space-time, we could establish a four vector that was given at every single point in space, okay? And that was described by those coordinates. So, then we also had another three vector where we did, where it was Latin letters. I want to write both of those, and that was just the opposite. That was everything without time. So 1 is equal to x, 2 is equal to y, and 3 is equal to z. And sometimes we'll write the three vector as a vector with an arrow, but not today. We're using different books. Different books have different notation, so we'll have to be careful about those overlaps. So that was what we did like one of the first weeks, and that was the four vector. But then we also talked about a vector space, a collection of vectors that add and multiply together by real numbers in a linear way. So we could talk about in a real vector space, we could have something that looks like a plus b times v plus w, where v and w are vectors. And that would be, a v plus b v plus a W plus BW. And now, something happens when we switch over from 3 vectors to 4 vectors. I should have mentioned that. And we talked about this last week too. Like, you lose things. Like, there's no cross product. Each vector is located at its point in space-time. And such like that. Now, is there an up and down in space? Well, there's a positive and a negative in direction. And those are all dictated by the, oh, bye, Astro Beer, take care. And the negative and positive determine the direction in space, just like they would do in anywhere else. And that is all in the unit vectors, which we'll talk about in just a second. Because every vector has a magnitude and a direction, and that's what we're interested in unpacking. So now we have a tangent space. We talked about the tangent space last time, and this was a set of all vectors associated with P in space-time. So if you had some weird manifold here, then there was a point somewhere where you could draw a plane that just touched this point, and on this point there was a bunch of vectors, and all of the vectors that make up this plane. So on this tangent plane exists this group of vectors, and it's all vector space because we have it there. So then, yeah, so anyway, so if we knew this, let me write it here, I guess. So I will write this down. I was kind of going back and forth on whether I'll write it down, but I will. We defined a vector component to basically be the derivative of the space-time coordinates with respect to this function parameter. So we'll know that the space is behaving a certain way because we'll have some function that follows of this parameter, and this parameter kind of dictates what's the space actually looking like. How is it changing at that time, at that infinitesimal small point right here on the manifold? And we can talk about the components of some vector in this vector space written like that, okay? So that was what we defined as a vector. We're gonna look at something very similar to this. And then we can also write it as a full vector, like I think it was Keebles was asking, Keeble 92 was asking, welcome Keeble, good to see you. And that was, is there a way to talk about an up and down? And sure, we can write a vector, like the vector is associated with this, but there's also direction in here. Now, if it's tangent, then there's only gonna be, a couple ups and downs. You could go this way versus that way, or you go this way versus that way. But those aren't necessarily particularly up and down. This is a tangent plane, so we're more along concerned about the plane itself. And that's, you can have a 3-dimensional tangent plane too, I'm pretty sure. What would that look like, calc math? Question. Okay, so then this would equal v with the component times some direction vector or unit vector. And that would determine the direction, okay? So now we did a bunch of stuff last week with like unit Lorentz transformations and things like that. We figured out that there is dual vectors, and dual vectors could act on vectors such that if we had an arrangement like this, if little w was a dual vector, then we could have A times B, which is a vector in this tangent space, plus B, which is a vector in a tangent space. Then this would be AWV plus BW, big W, and whatever this would be an element of reals. Okay, so in other words, you get a number, get a real number. And that's like so basically, can a tangent space is a tangent space, like, can you have more than, I guess I'm just wondering about this in the tangent space. Does that have to be a two unit vectors, or can you have more than that? You should be able to have more than that, right? Like 4. That's my question. I'm not 100% sure. It's a Greek letter, so I'm assuming it's going to run over 0 through 3, right? But I guess I don't know exactly what that would look like. Yeah, you will have 4. Okay, I assume that, but I don't know what that looks like. You know what I'm saying? Because it's a tangent plane. A photon checks with your hotel bells. Can you take your luggage? Photon implies not having I'm traveling away. Come on. Tangent space should have same dimensionality. Hyperplane. Okay, so there's an actual thing, so it's a hyperplane. Okay, I'll have to look into that. Cool. I haven't gotten into that part stuff yet. Interesting. But that's what we get to, and now we want to switch it over to tensors, because we have a good way to go take that inner product.
This is one of Eric's episodes.
There he is. Thank you, Tyrion. All this assuming you are embedding the 4D manifold into something, but you don't have to. Okay. I think I understand that. Let's keep moving on. So can we have something that's more general than that? We have a dual vector can take a vector to a real number, but what if, can we have something to take two vectors to a real number? Can we have something to take three vectors to a real number? And yes, we can. So let's consider the metric tensor. That's a good one. So the metric tensor is going to be, some tensor of A and B, where A and B are vectors. And what does that look like? Well, we're going to define that by A dot B, which is going to equal, and now we're in Hartle, guys. We are switching out of Carroll and into Hartle. So this is going to be the metric tensor times A alpha, B beta, and because we are taking this linear mapping, now this is a linear mapping of 2 onto 2, this would give us a real number, right? There's nothing to write after that. But this is just an example of a rank 2 tensor, which we're going to talk about ranks right now. This is an example of a rank 2 tensor, which basically takes two vectors and then it's a linear mapping onto two tensors there are two vectors that take them into real numbers. Okay. So now what is rank? Because we just said rank 2 tensor. What is rank? I think rank's important. So let me say what Hartle says, because I really like this a lot. The straightforward definition of rank is as follows: the tensor of rank R is a linear map from R vectors to real numbers. So that makes a lot of sense, right? If we have a scalar, then we just multiply it by scalars and we just get scalars. Those are real numbers, right? If we have a vector, then we have a 1-rank tensor multiplied by a 1-rank tensor. A dual vector times a 1 vector will get you a real number. How about a metric? The metric is a rank 2 tensor, so it can map 2 vectors onto reals, and that's what we have when we do this. Okay? So we know that a vector is rank 1. These are just examples. This is a little bit example heavy today, I think, which is good. A scalar is rank 0. And the metric, as I write the metric, is a rank 2 tensor. Okay, and I think these are very important tensors for us, and these are things that you've seen throughout high school and college and things like that. Every time you dealt with a vector or a scalar function or anything like that, you've always been dealing with tensors. So how can we construct them? Well, there's a bunch of ways to construct them. We can think of the following rank 3 tensor as a tensor that takes some vectors A, B, and C. Now in this, there's a dual vector as well, and we won't worry about it too much, but we'll talk about it. Okay, so let's look at the following tensor. We can write some T, A, B, C, where these are all vectors. Oops, I wrote BB. And that could equal T alpha beta gamma times A alpha B beta C gamma. Now here we have a tensor where we have two vectors and a dual vector, right? And writing this rank 3 tensor, we can do that. And this tensor, this rank 3 tensor, will take these 3 vectors into you need color chalk. Why? Why would I need color chalk? I have lots of color chalk. They will take these 3 vectors and into a real. So this tensor, whatever it is, can map onto those 3 vectors and turn that into a real. Hold on, I'm going to shut this. Sorry for the loud noise. So what can we do with this? I mean, this is not the most helpful thing, right? is there a way where we can talk about changing these so that it's not all in weird ordered? So is there a way we can change this so that they can all be top or bottom? Like, i.e., can we move the indices around? And it turns out we can by using the metric. So one way to think about that is now we can take a vector and we can act on it with the metric. So we have a vector c to the delta. We can act on it with the metric. If we have vector c to the delta, we can act on it with the metric tensor. And out comes a vector with a lowered or raised indice, depending on whether or not our vector is covariant or contravariant. This vector is covariant. Okay, so that will help us act on a vector to lower an indice. Now, that means that we could rewrite our vectors. T of alpha, beta, and gamma is the one that we want. So we can actually act on the original tensor with the metric gamma delta, T alpha, beta, delta. And these indices, they're just dummy indices, so don't get caught up on what the alpha, beta, they're all rearrangeable. You can just rearrange them, or not rearrange them, you can label them. You can relabel the, you can relabel the, oh wait, I wrote that wrong, hold on. It's not a gamma gamma, it's gamma delta. Sorry. And you can rewrite them however you want, so don't get caught up on like, oh, there's a delta there, but now it's not delta and blah, blah, blah. You can just rewrite alpha, beta, gamma as alpha, beta, delta as long as all the indices get changed appropriately. Okay, so now what? Well, if that's the case, then this finally gives us our tensor of A, B, C. And I say that as I do it, now we can rewrite this as alpha, beta, gamma, A alpha, B gamma, B beta, and C gamma. And now they're all raised, and we don't have to worry about that last tensor. Whereas we reestablish this as now the metric times the original tensor. So there's something will happen. This is a change. We are mapping the tensor, right? We are mapping this metric onto this metric tensor onto this tensor, the 2 onto the 3, to change it into a different third rank tensor. Have you already talked about the implicit summation of Einstein's notation? I did. You have to relabel them each term though, or the expression loses meaning. Exactly, yeah. What's the significance? Tyrion asks. Well, that's how you, so the implicit, I don't know if I've done the implicit summation of Einstein's notation. So the up and the down are what is going to act on each other. So like, for instance, like if I'm going to be acting this tensor onto these vectors, this alpha is going to act on this alpha, this beta is going to act on this beta, and this gamma is going to act on this gamma. In order to contract them, remember this is going to be some element of real numbers. So in order to get those vectors and the tensors into real numbers, I need to contract all of the like indices. If these were like, say if I had alpha, beta, gamma, and then alpha, beta, delta, or something like that, then this would not equal some real number. The two indices would contract, and I'd have a different tensor. Okay, so what does it get? So this essentially shows us how we can raise and lower indices with using certain tensors. And that's nice. So let's do an example. This is a fun example, I think. Kind of shows some power behind these things. All right, so let's consider the metric tensor. Okay? We can write this in the following way. Suppose we had an upper indice and a lower indice, okay? So we're just gonna raise an index, lower index, whatever. How do we do that? Okay, so we can define this as the following. We'll take two metric tensors and act on each other. And then they'll have one index that will contract. And then what's left is, so we have two of the metric tensors, and if you contract one index, the gammas, like CalcMath said, you sum over those, and what you get is this new thing. And what is this new thing? Well, this is the inverse of the metric tensor, and this is the metric tensor, so you're multiplying the inverse of the metric tensor times the metric tensor, and we know that this is actually equal to delta alpha beta. Okay, when you multiply the inverse of the metric tensor by the metric tensor itself, you just get a Kronecker delta. So that's nice. So now we've realized that this is just a Kronecker delta reposed as, you know, some weird version of metrics multiplied together. So can we do anything with that? Well, sure. CalcMath. So can we change this to can we do anything with this? Well, sure. How about if we have the metric tensor beta gamma, and we multiply it by one of these things, alpha gamma, then we can get gamma beta, or G beta gamma delta alpha gamma, since that's this. And then when you act on these can contract and go away. And what do you get? You get a single metric tensor with everything upstairs. Okay? So there's some convenient things you can do with this, as far as like getting things worked out so that you can get rid of some of this stuff. As long as these tensors are together and you can multiply and contract them, then it's good. So can we talk about constructing some different forms of tensors? So let's consider a rank 2 tensor, okay? So this is a rank 2 tensor that you might not have thought is a rank 2 tensor, but let's write it down. Again, we're playing with indices right now. That's most of today. We're gonna write down a bunch of playing with indices stuff, just so we can figure out how to contract things appropriately. This is rank 2, right? While you have a tensor of rank 3, it's acting on a tensor of rank 1, a vector, and you can and one of the indices is the same, so you can contract it away, and what you get in the end is a tensor of rank 2. How about a vector? Now this one I think is much more important. So let's start with a dual vector. But we can write the vector as a series of tensors. How about writing a vector as a tensor rank 3 multiplied by 2 vectors? So now there exists some way where we can actually take a look at an object by multiplying 2 vectors by a tensor of rank 3. Can we do something else? Well, sure. Now we have to talk about something kind of tricky. This one's a little bit more tricky for me. And this is all we have today. 4 pages of notes, about a half an hour of stuff. It's not much at all. And this is the coordinate basis transformations. Now, we have to think of another way to write down a vector as a directional derivative. So we're going to go back and revisit our last definition, but now, instead, we're going to talk about how a vector is going to act in a tangent in the tangent space. So let's consider a vector can. Let's see, what does this say? So what does Hartle say? He says another way to write down a vector is as a directional derivative, such that for any vector A in the tangent space, A can be defined as the component of A times the derivative of the spatial component. Okay? Therefore, you can basically write a vector, and this would be like similar to the gradient, I think, right? This would be similar to the gradient. In 3D, you can have antisymmetric, which gives cross product. Interesting. I'm sure the mixed metric is the Kronecker delta in the space where the metric loses symmetry. Yeah, I don't know. What's a cross product? Is that a cross product? Oh, in 3D. Oh, in 3D. Okay, yeah, cross product. Okay, so that's a normal cross product. Okay. Excuse me. Okay, now, so this means we can write a coordinate transformation from one coordinate system to the other coordinate system. How do we do that? You might be asking. Well, so here's the second and last example. How are coordinate basis components, of a vector A related from one coordinate system to another? So suppose we have two sets of coordinates. A is in one set, and x of alpha, wow, x alpha is one set, x prime of alpha is another, and we know the connection between them. Okay, so consider like, that is, we know x prime alpha acting on x. So consider something like, switching from Cartesian to spherical, I think would be a good example of this. Okay? Is that a good example of this? I think that's a good example of this. Maybe somebody can have a better example of this. So then what can we do? Well, we can write, basically, start with our vector. We'll start with our vector A. Actually, let's start with it somewhere else. Let's start with our vector A, written as the components times the directional derivative. This is the part that boring math professor is going to love if he was here, or anybody who's really highly, calc math is a PhD too. Anyways, highly mathematical, loves this part. Okay, so we can rewrite this. Then we can multiply it by 1, and we get A to the alpha partial with respect, or partial D, or X, prime to beta, X alpha. It's out of the way a little bit. And then partial with respect to X prime beta. We can define this as that transformation from states, or from coordinates, from one coordinate, or the relationship that we know is basically what the step we need to get to here. We need to use that relationship that we know. Now here you have this component of a vector, a to the alpha, times the derivative of the new coordinate system with respect to the old coordinate system, and then times this derivative right here. You have that derivative right here again, so we can cancel that out on both sides and find out that that the components of a vector in the tangent space are equal to dx prime beta dx alpha times a to the alpha. So that's it. So we can transform, we can act on this with this derivative, the spatial derivative, and from that we'll get a new, we'll get a different coordinate system, or a different, we'll get the vector in the different coordinate system. So that is how we do a coordinate transformation. So I can introduce Levi-Civita. I didn't write notes on this, but I can definitely introduce it, I think. So if I struggle through this or say something wrong, please correct me on this. But there is one very important tensor that we're going to need to understand. And what does this say? So related to the Kronecker delta and the metric is the inverse metric. So we talked about that. A type of 2, 0 tensor defined unsurprisingly as the inverse of the metric. And we found out that if we multiply the inverse tensor, or the inverse metric times the metric, that's the Kronecker delta. We saw that. In fact, as you can check, the inverse metric exactly has the same components as the metric itself, which is also very nice. This is only true in flat space in Cartesian coordinates, and will fail to hold in more general situations. There's also called a Levi-Civita tensor. All right, so the way that the Levi-Civita works is, remember how I wrote one way to think of the Kronecker delta, where you have an alpha and a beta, is when alpha is equal to beta, you get 1, and 0 when alpha is not equal to beta. So that was one way to think of it. So we're going to write the Levi-Civita tensor the same way. That's the way that Carroll has it in his book, and I like it. And it's a very interesting tensor. I forgot this is how you can write a cross product like this, though.
But you never believe me. Never.
That computer sounded very emotional when he just said that. Plus 1. I would believe you if it was a coding thing.
I am not emotional, you are emotional.
So it's all about permutations. So is an even permutation of 0, 1, 2, 3. I should write if. And minus 1 if mu, nu, rho, sigma is an odd permutation of 0, 1, 2, 3. So for instance, and 0 otherwise. So for instance, if you have these as 0, 1, 2, and 3, so if it's, see, he doesn't have a single example in this book. I wonder if Hartle has one. Let me see. Sure, we could probably do that. So in, should I just do 3 by 3? Let's just do 3 by 3. We can probably work it out pretty quickly. So let's say xi, xj, xk, yi, yj, yk. And then can we do the cross product? So the cross product, when I do the determinant, so the, so this is the determinant. Christoffel symbols, we will get into them. But yeah, it's the determinant when you have the unit vectors up here. That's what I meant to get. Okay, so we can write this as, and then you have to determine the inner one. So this is I, j, y, k minus x, k, y, j all times I. And then it will be minus. Right, is it minus? No, it's plus. It's plus. Next is going to be xi, yk minus xk, yi times j. And then it's going to be plus the last one, which is going to be xi, xj minus x j, oh wait, I wrote too many x's, hold on. x, I, y, y, j, x, j, y, I, k hat. Okay. Natural units, Enbro. Nice, welcome, welcome. So if you are here from Enbro's channel, my name is Eric. We do physics on this channel. Right now we're doing some tensor fun, some tensor analysis. Is there a reason why you have a 4-index Levi-Civita symbol? No, that's just the one that Sean Carroll listed as a 0-4 tensor. So a rank 4 tensor, I don't know. Maybe to be inclusive? I don't know. So we can write the Levi-Civita as, instead of a 4, we could write it as a 3, and the same process applies. It's just between 1, 2, or 3. So if we wrote the Levi-Civita as a 3, tensor, we could do ijk. Rewrite that, and in the so plus 1 if even perm ijk, minus 1 if odd perm ijk, and 0 if otherwise. So if like any of them match at 0. Thank you, Tyrion. The second one should have a minus. Should it? Have I forgotten how to do this? You're right. Man, it's been a long time. Very good. Well, we would have found that out very soon because you can write the cross product as x vector cross y vector is equal to Levi-Civita of I, j, k times x I, x j, right? Or x I, y, j, right? So what happens then? So let's figure out what happens. So let's check with our first term. So in this one, we have j, k, I. So is that even permutation? Well, sure. I, j, k. All we have to do is take the I to this side, and that becomes j, k, I. So that's good. So far, so good. You can write these. Actually, it might be easier if you wrote those as these vectors we used last week, instead of writing them as the hats like that. But either way, whatever is more convenient for you. Next up, proper copper. You smell dinner. Nice. So next up we have k, j, I. So now how do we get that? Well, we have to take, it's k, j, I. So that would mean we'd have to switch these two. So we cannot make k, j, I out of I, j, k. We have to switch them without switching everything. So we can move this over here, but then eventually we have to switch k, and then we get k, j, I. This is what we call an odd permutation. You can't get there through cyclical methods. You have to move, you have to permute something through it, right? Okay. So that's a negative. So now for this one, we get a negative, which we do. Perfect. Well, that's equals. Good. Let's check the next one. Next one is negative, and we have I, k, j. Well, again, now we can't, if we have I, j, k, we have I, j, k. The way to get that, obviously, is by flipping the j and the k. So again, we get an odd permutation. And we get a minus sign, so that's good. Next up is a minus minus, so that's plus. Let's check that. It's k, I, j. Sure, all we have to do is take I, j, k, and then we'll move the k to the front, and we get, so through cyclic motion, we can rearrange that and we get positive. Let's check this one. This is positive, so I, j, k, that looks good. And then lastly, j, I, k. The way you get that is switching the j and the I. Okay? And in order, so that's an odd permutation. So these are all of our tensors. Let me say hello.
That really hurts my ears and my soul.
Oh, it's probably really loud now. I'm sorry. Probably all of the music was very loud for that because I had it turned up. I'm sorry. Profelt Santos, welcome. Welcome to the channel. Thank you for the follow. Okay, now that is what we have for tensors today.